Well, welcome to the anatomy of a published paper leveraging Google Earth Engine for impactful research. I'm Erin Trosham, and I'm joined by my co-presenters, TC and Sampira, and I'll let them introduce themselves. What? Sam? I know, it's okay. And we're here to talk about research. And so we wanted to start with that there are many ways to do impactful research. And this talk is going to talk about or focus on peer-reviewed publications, but we'll have time at the end to talk about what does impactful actually mean and how do we navigate that in the research world between peer-reviewed publications, apps, and then also data sets and influencing policy and communities. So the session goals are to demonstrate the power of Earth Engine for enabling high-impact published research, providing guidance on best practices for rigorous, ethical, and reproducible Earth Engine-based research, and inspiring attendees to apply Earth Engine to amplify the impact of their own work. So our agenda is we've got 6 sections. The first one will be going over what is impact and impact in the context of scientific publications. Then we'll be talking about generalizability, the advantages of Earth Engine to ease data access, computation, and presentation, framing. We'll talk a little bit about approaches, data, multidisciplinary approaches, and practical applications. Then we're going to spend some time going through reproducible fairish principles, and so that includes setting up Earth Engine, understanding data, code sharing, and version control. Then we'll cover the ethical considerations of and engagement in individual, social, and subject lenses, and then we'll have some time for discussion at the end. So impactful, and what does that mean? So when we were talking about this talk, we put this slide because we published a paper this summer. We're all co-authors on it. It's called The Pillars of Cloud-Based Earth Observation for Science Education. And I put this figure on because it illustrates really well in both the education but also in the research and the peer-reviewed publication that we've gone from doing traditional Earth observation where we were downloading and processing data locally, we were doing a lot of manual interpretation, and we were really focused on local to regional scales. And through the dimensions of fundamentals, ethics, and engagement, we've now transitioned to the cloud-based version of that where we do cloud-based analysis. There's a lot more opportunity for automation and iteration, and we're also able to look at regional to global scales. And so with that, we'll start off with TC talking about impact.
Hello, everyone. I'm TC. I'm an earth scientist at the Pacific Northwest National Lab. And I'll be giving an overview of, based on my experiences, based on my work, what I think is impactful, what is considered impactful from the peer review publication space. So I'm going to be talking a little bit about controllable and uncontrollable factors when publishing in high impact and general interest journals. And I kind of separate these out because you can have high impact journals which are domain specific. So in the remote sensing community, you have remote sensing of environment, which tends to actually have, if you think about it in terms of impact factor, it has a higher impact factor than many of these general interest journals like PNAS. In our field, it's like Bulletin of the American Meteorological Society and so on. But then you have the general interest journals, which I think there has been a focus on trying to get published in these journals. This includes, of course, Nature, Science, all of the Nature portfolio journals, the Science portfolio journals. Recently, Cell started their own bunch of portfolio journals. And it used to be that general interest journals were for a particular general audience about certain topics that the general audience would like or appreciate. However, I think with the incorporation of a lot of these Nature portfolio journals specific to domains, so you have this mix between high impact and general interest journal within broader domains. Now, there are a lot of controllable factors, and this is based on both reviews I have done. I have not been in the field for too long, 10 years or so, so I'm sure there are people at the conference and maybe even here who have more experience than me, but I was asked to give this presentation, so I'm giving it. But Basically, I think, like, based on the papers I've reviewed, the papers I've published, and the papers which have been desk rejected and gone through like the peer review process, in the kind of geospatial space, I think these are like the main criteria for when it comes to controllable factors. And based on these, like, I would actually attempt to submit papers to similar journals, either high impact disciplinary journals or general interest journals. So first is scale. And I think the scale kind of comes down to two different things. First is who cares outside the subfield. And this is also relevant for something like remote sensing of environment, where you have like specific facets of remote sensing within the community where like people are working, say, specifically on, my expertise is urban areas, but people working on like deforestation, people working on like water bodies. But for like some of these high impact journals, it has to be kind of relevant beyond that subfield. And the other is how many people may be affected. So generally, and maybe you have seen this, that a lot of the high impact journals are global scale studies, especially like it's well known that Nature likes global scale studies. It's also well known that there are biases about certain regions over another. So you can have regional studies over the US get published, or Europe get published in general interest journals, but the same thing over India or parts of Africa may not get published. So there is that bias that's well known. But that kind of comes down to like geospatial science and remote sensing, where you can kind of scale up and do the same kind of analysis regardless of region in many cases, because the data sets usually are pretty for large regions. Then it comes to the novelty. And I think novelty can be there are many ways to kind of think about novelty, and a lot of that also comes through framing, like how you frame your study within the existing literature. But I think the big ones are the results surprising? Like if you know like something is well known in the field, is this challenging that best understanding? The other is does it resolve an ongoing debate in the scientific community? In the climate change literature, this has been like one of those things. Like we talked a lot about aerosols in the past because we had large uncertainties in our understanding of the aerosol impacts on the climate. And finally, does it propose and or test a completely new hypothesis? This relates to like suggesting new mechanisms for understanding the physical system, the natural system, and even for applications when you're trying to use new methods to implement on particular topics. Then it comes to the methodology, where you have do you have a sufficient fundamental methodological advancement? So this is a kind of a choice between like, is it an incremental study or is it like a leap forward? And a lot of this is kind of subjective and depends on reviewers. And I'm gonna talk about like the uncontrollable factors in the next slide. And finally, does it reconcile issues across different techniques in the field? And this is kind of known in many fields where you have, say, top-down versus bottom-up approaches, and they don't agree with each other. If you can find a way to reconcile them, they tend to be publishable or more likely to be published in the general interest journal. And finally, presentation. And this might seem a little critical, but when I think about submitting a paper to, say, Nature Communications, Nature Climate Change, I do think, like, is this going to become a news article? That may not necessarily be true, but I think that's more true in the climate space than in, like, say, theoretical physics, where, incidentally, not a lot of papers get into Nature for theoretical physics. And finally, like, how you kind of present your work. Like, are you writing for people outside your field? And this is just to, like, make that particular paper more palatable to people who may be reviewing it who are not in your specific subfield. This often happens in, again, science and nature portfolio journals. And then you come to the uncontrollable factors. First, the peer review process is kind of what we have right now. And unfortunately, like when you think about the statistics of it, you are asking 3 to 4 people, sometimes less, if you have been submitting papers in the last couple of years, to kind of give you an idea about the quality of your work. And that's a very small sample size. And that's particularly a small sample size when you're sending this to journals where the editors are not practicing scientists, which is, again, often happens in the general interest journals. So yeah, that's the second point, that The reviewers may not be trained in your subfield and may disagree with the implicit assumptions in the field. For instance, I'm going to give you an example. We published a paper in Communications, Earth and Environment where we showed that urban areas are warming faster than rural areas. So what happened was on Twitter, a lot of climate deniers kind of took that study and started talking about how urban heat island effect is the primary reason for background warming. But within our field, when we talk about rural area, we are talking about a very immediate region right around the urban area. So it's a very small area versus like the background climate, which is everything other than urban, where urban is like 1% of the global land surface. So you cannot really compare those values with what's happening for the Earth's surface as a whole. And this is a problem in, I think, general interest journals in like when you publish it for that kind of audience, it's very hard to keep that nuance in mind because you're not publishing for your own discipline. You're trying to publish for everyone who can read that paper. And of course, like, there are cases where a reviewer may be working on a competing theory. This does happen. You may get scooped. This is kind of unfortunate, but it is part of the process because ultimately scientists are humans and they have certain conflicts of interest. Then you come to competition where, let's say, you are competing especially in like, this is true for, again, both high impact journals within the field and within general interest journals where you are competing against other papers for a limited slot. And in many cases, these limited slots are not physical limited slots nowadays because everything is online, but more of a reputational limited slot. Like, you don't want to have your acceptance rate too high. Like, I don't know if you have seen, like, sometimes you will have a rejection where the reason for the rejection is it could have been published, but it would take too long to get published. So they want to kind of keep their time to publication low because, again, all journals are also competing against each other, their own market there. Then there's the case of like another group getting to a result before you, which will, of course, impact the decision. And then finally, potential conflicts of interest with reviewers, which reviewers are supposed to declare, but maybe they don't. And finally, biases. Individual scientists have biases and their evaluations have subjective components. And this is particularly true if people have issues with studies coming out of particular regions where they don't trust the data, and that does happen. This happens if someone does not like a method for whatever reason, because of disciplinary reasons. For instance, in the earth science field, it's actually somewhat hard to get pure ML papers published because earth science has a lot of process-based modelers who don't necessarily like pure ML-based papers, so they're kind of against it. And then there are systematic biases based on region of interest, excuse me, topic and background affiliation of the authors. This is also very well known that there have been multiple meta-analyses which show like people of particular, or like professors of particular institutions are disproportionately publishing in these higher impact journals, or that if you publish a high impact journal early on in your career, you are more likely to keep publishing in those journals because part of that has to do with like the editor, like your relationship with the editor. So there are like a lot of human components there, and when there are humans involved, there are biases. So it's not like an objective process by any metric. And then the final, I like this, like truly revolutionary work by definition cannot be accurately judged in the present. That doesn't mean anything that's rejected is going to change everything, but it does mean that there have been many cases where really fundamental changes have not been published in this journal. Like recently, the mRNA paper was initially, for instance, rejected from Nature. It was still published in a very good like disciplinary journal, I think Immunity, but it was rejected from Nature. And there are multiple other examples of a lot of like the physics Nobel Prizes that the original papers were rejected from Nature and Science. So if your peers are not in a position to actually judge your work because your work is ahead of their time, then it probably won't be published. But that doesn't mean that you should think that your work was ahead of everyone's time just because it got rejected. So another thing, so that's just the publication phase, right? But there is publication impact after publication. What I mean is that ultimately when you publish something, what matters also is how likely it is to get cited, how people are citing your work, and also like how it's actually affecting the field. Because number of citations does not always mean that it's positively or negatively affecting the field. I have two examples here for two papers I was involved in 2021. They're both published in Nature Communications within a week of each other. And one has been cited 6 times, which is so bad. And the other has been cited 240 times. So, and part of that has to do with like how many people are in the field, how interesting it is to the overall community versus the editor who decided to send it out for review. And also, it does depend on like who is doing the work. Like if you are already well known in a field, in the first paper, like we were not precipitation people, any of us. So it's very hard to get cited if people don't already know you. On the other hand, like for the urban stuff, I have been doing a lot of work on urban. We had previous similar papers on urban, so it got cited. Another example, this paper published in 2019, it's not, this is a good journal, a good disciplinary journal, but it's not like, this paper was also rejected from remote sensing of environment after one round of review, just letting you know. It has 259 citations now. It's the most cited paper I have. And both like this paper and the paper above are in like the Web of Science highly cited papers index since 2022, which is weird that it started being in the index in 2022, not before, because sometimes the citations kind of ramp up later on in time. So that kind of brings me to like the advantages of Earth Engine to kind of generalize some of your analysis to make it more feasible to publish these high impact journals papers. I think the big one is that, as Aaron mentioned, that we used to do these analysis where we would download the data and we would try to analyze the data. We would archive all of the data available and then publish based on the analysis on the data. But this has become increasingly hard. This animation shows the number of like satellites kind of orbiting. They are not all Earth observing satellites. Most of them are not. But it just shows like just the number orbiting the Earth. And a lot of them are kind of gathering data. So there's been a kind of an explosion of data in the last, say, 20, I would say, even more 10 years. And there's going to be more. Like I just learned today about like a global hyperspectral data set from the German Aerospace Agency, which is like insane at 30 meters. But let me see. How do I go to the next? Okay. And similarly, like from the different Earth observing systems like the European Space Agency, so this 150 terabytes of data per day is actually delivered data, not like produced data. But I think the actual number is closer to like 3 or 4 terabytes per day nowadays. So there's a lot of data being generated every day. Similarly for NASA, back in 2016, they had 12 terabytes of data per day, and the current archive is at 40 petabytes. And by 2025, you have multiple missions kind of planned through NASA, and they are expected to go up to 245 petabytes. That's like a ridiculous amount of data to process on a desktop system. And in addition, you have like a lot of companies in the commercial space who are launching their own satellites, who are also basically collecting data and releasing them, and you basically have too much data to process using traditional desktop-based software. So that kind of brings us to kind of the fourth paradigm of scientific discovery, where it's easier to move your question to the data rather than move your data for analysis. And I think that's why like Earth Engine is a really nice platform to do that, because I think the big advantages of Earth Engine is the data catalog, the compute available to you, the assets and data ingestion, and then finally, I think this is part of like presentation, and I really like this feature, is the web application development through the JavaScript API. So I'm going to just give an overview of these. So Earth Engine currently has, I think we are at like 90 petabytes, but it's probably, a year old maybe. Over 1,000 data sets and around 100 data sets being added per year. And if you kind of go to the Earth Engine asset catalog. You can see some of the examples of the data they have. So they have a bunch of climate and weather data, reanalysis data sets, gridded products, even like downscaled climate model projections, stuff like that. And you, of course, have the imagery like MODIS, Sentinel, Landsat. And then you also have a lot of derived products for, say, surface properties. And that's just like in the data catalog. And Earth Engine, of course, takes advantage of Google's computational infrastructure, where you can essentially run calculations on the cloud, which makes it much easier to scale up your analysis compared to doing it on desktop softwares like, say, ArcGIS, QGIS, and so on, or even like your desktop Python environment. I have kind of an example here, and it's like a very simple example, especially if you have been working with Earth Engine for any length of time. But basically, this is a script where I'm trying to see the change in vegetation cover based on the MODIS continuous vegetation fields. So I do this first for like New Haven, Connecticut, and it's almost instant. But then I want to like do this globally, and I can, let me run this. And it is almost taking the same time, which is insane. And I bring up this example, and like MODIS is not particularly data hungry or compute hungry, like especially for Earth Engine. But back in 2015, when I was doing my master's, I did not know about Earth Engine, which is good and bad, and I will come to that at some point. But I was using MATLAB for satellite image analysis, so I would download LST tiles, land surface temperature tiles over my study region, and it would take 20 minutes to process one tile. And now I can do global analysis of the entire MODIS archive in a couple of minutes sometimes. It depends on the exact structure of the data, but it's unbelievably fast in comparison. So this kind of scaling up where now everybody can do global scale analysis. Earlier it was mostly restricted to folks who had access to a supercomputer or had very high, fast internet connection to be able to download and archive the data. And all of that has kind of been, those requirements have been minimized due to Earth Engine. Go back here. I will give another example here for an analysis I did. Like this is to create like, I talked about the urban heat island effect. So basically one way to create the urban heat island effect or calculate the urban heat island effect is you start with an urban cluster and you create these normalized buffers so that the buffers are basically some function of the urban area. And what used to take a long time to do before in desktop software, now I can do globally. So this kind of shows like a workflow of how I did it, but basically now I can do global scale iterative buffers to create this for, I think it says like 80,000 clusters globally. And the interesting thing is like, there are no studies of 80,000 urban clusters and their urban heat island. And I have been sitting on this for 4 years and I haven't published it. That's the other thing, like I am sitting on probably 5 papers worth of data and I just don't have the time to write it up because the analysis part has been kind of made like marginal. So, probably you will be not working with just MODIS data like Sentinel and all of the 10-meter data sets, all of the, if you're working with Planet data or any of the private company, commercial data sets that maybe you have access to. I would suggest like this chapter and this book as a whole. I know Rebecca already mentioned it. So I was one of the authors. I wrote the Urban Heat Island chapter. But the scaling chapter I think is very good for understanding how to like optimize your calculations using Earth Engine, especially when you start working with larger and larger data sets. So I did talk about like the data catalog, but in addition to that, you can also take advantage of your Google Cloud Storage when working with Earth Engine. You also have an internal asset quota where you can upload your own data set. It is by default 200 gigabytes, 250, but by project. And I mean, you can add more projects and get 250 per project. But if you have a specific need, there is a form to fill up to ask for more data allocation or asset quota allocation. But I'm going to be also kind of plugging these 2 other sessions. Both are tomorrow. And Sam is co-presenter for both of them, but one is about Earth Engine data catalogs, including the new implement kind of.
Yeah, talking about the preview, but we're also talking in general about the community catalog.
Right. And then about getting your data into and out of Earth Engine. And Sam will also talk a little bit about that, those things today as well. And finally, I think this is like the last part is the presentation. A lot of, I have usually published web applications with my papers, especially for like large scale data sets. And I think a lot of the data sets became more available and more open to the public and more visible due to the web applications. You have examples for the global forest change, which of course most of you probably know. You have the Global Surface Water Explorer. There are already a few tutorials on creating your own web applications. So there is this community tutorial I wrote this year on developing this web application to understand air pollution, PM 2.5 pollution, and you can kind of go to this link and go through the steps. I can also go here and kind of show you. So basically what it does is it shows the exceedance. So yeah, this was just like a side project where I realized like the WHO had reduced their standard for annual concentration of PM 2.5 from something like 20 to 5, which is a huge decrease. And if you look at some of the air pollution data sets, 98% of people now live in regions above that threshold. So this exceedance factor basically tells you how much higher, like in terms of like how many times higher the actual value is compared to that threshold, and can reach like 20 times in North India, for instance, and parts of China. And you can also see like the PM 2.5 concentrations. You can click on it and get like charts, automatic charts being generated using basically showing the change over time. This is all based on one data set. Additionally, like you can actually click on this and download the CSV if you want, so you can get the data for this particular chart. There are better ways to get data out of apps, and usually getting data out of apps is not what I would recommend. There are other more easy ways to just like send it to Sam and he will upload it to the awesome G community catalog. But this is kind of an example. And with that, I will stop my spiel. And Erin.
So we're going to take a little detour briefly to talk about framing, which is definitely something that I think a lot about. And so I took a little bit of time to put 4 of the different approaches that are common, and I've definitely used these when thinking about framing and thinking about having impact. And so one of them is just simply innovation. So you can use Earth Engine to handle data, you can do machine learning, and you can summarize. That's a pretty simple formula for doing high impact work if you find niches and you're strategic about what you're doing. Number 2, you can consider the effectiveness of the data. And so there is a lot of disconnect, especially I have some Arctic researchers in the house today. There's a lot of disconnect between a lot of the global models and how they actually work and function in a lot of different regions, and in particular, that tends to be an issue in our Arctic areas. So there's an opportunity to compare observation networks with satellite or model data, derived data sets, and consider, should you be using this? Is it possible for you to fix it? Is there something that the global people need to know next time when they're producing this data set? That is very important because, like TC mentioned, there's been this big push towards these global data sets. They're definitely used for large-scale comparisons. They're used to draw attention to issues. They're used for humanitarian resources. And so the effectiveness is really key. Approach number 3, you can always invite more people to your party and address multidisciplinary challenges. And so when you start to move into the decision-making world, at the end of the day, what matters is that you make a decision. If you like work or you happen to live with managers, they make decisions for a lot of different reasons. Some of it is how they feel that day. Some of it is the access to the information. But the reality is that things have to get done. And so when you take discipline team, which a lot of Earth observation data has often been more driven by disciplinary approaches, and you look at bringing in people with different expertise, then you have the ability to not only harness the power of the different training that everybody had, but address some of those harder questions a lot more effectively. In my experience, this can look a little different than you think too. So I've had the opportunity to work with some psychology students and professionals, and it's been incredibly valuable in thinking how, like, the data perception, how we can improve our visualizations, what other social dynamics. It's really useful to have an economist on your team if possible. There's a lot of opportunity in the Earth observation space in doing high impact work and making it multidisciplinary. And on number 4, transferring for practical applications. So it's similar to number 3, but it's a lot more where that rubber hits the road in that decision making. And so I always joke that you can spend your time improving an ingredient, or you can rewrite a recipe, and you have to really understand what it is people do before you can understand what the opportunity is in that space. So for framing, the biggest thing that I think I've found professionally is that it helps to have a really big network. It helps to have people that you can ask questions to, and it helps to get sometimes what I'll say is negative feedback, like, that won't work. And I really appreciate that feedback because I want to know why. And then I want to know from their perspective what they thought, and then if that's necessarily true anymore. And sometimes those challenges still are true, but there are definitely things that we can do about it. So I also thought that I would show a fun thing because I've been thinking about this for a long time, actually. So when we're doing framing, there's a lot of new tools and new opportunities for looking how to find those niches. And so I have to say, when I do framing, I totally do this. I tend to do like a pretty big read on an area. I tend to look at, like, is there, like we just talked about, like a method that we can improve? Is there a data component? Is there a visualization that's missing? Is what's actually happening getting translated? But in taking that really broad approach, things just got way more exciting in the last year or so. So I've got up here some examples. I made some knowledge graphs, actually, from our different data catalogs, because if you're looking to do high impact research and you work in Earth Engine and you have all of this data and all of this compute, like TC mentioned, there's just a ton of opportunity. So these are not exactly equal knowledge graphs, is what I'll say. So I used a platform called Infranotus, and I pointed it at the community catalog website, and then I pointed it at the community catalog website and the data catalog. And what I noticed, and I was doing some editing of these, is that there is definitely some trends that like come and get picked up. And this was like just my like first flash at it. And it was a really interesting approach to start looking for some of where there are relationships between things. And so, like, obviously land cover is a huge thing, surface is a really huge thing, climate is a really huge thing, and you see it reflected in both the community catalog and then in both the community catalog and the data catalog. And so none of these are really that surprising. But it was really interesting to start to look at how the data sets are like clustering together and what you can start to like think about in the intersections. And so one thing that got pulled out is that there is definitely the ability to start looking at some of the urban environment and water, actually, especially in areas of Africa. That came out where there's a lot of impact. There is another key difference between these graphs, actually, which is that when you put the data catalog, the Earth Engine data catalog, suddenly radar data starts to pop up. And that's not actually present in our community catalog, which is interesting. That with the climate, there's a lot of like weather and prediction and deterministic. That's kind of interesting. One thing that was also getting pulled up by these knowledge networks or our knowledge graphs is the connection between looking at wildfire and then looking at land cover, which is pretty obvious. But they pointed out that there also is a bit of a disconnect to the elevation data, actually, which I thought was kind of interesting. So we've had a lot of new elevation data proliferate in this space. And the thing, like, they haven't, some of the modeling is working together, but the actual data sets are sitting relatively apart right now, which is kind of fascinating. So I put these examples out here to, I guess, illustrate that there's a lot of different ways to think about things now, including that you can go and scrape websites, you can scrape papers, and really take the time to think about the harvesting of large information and some of the trends that you can see, and also what's missing necessarily. And you can do that from both the paper side, or you can do that from the published data set side. So it depends on what you want to see. Personally, I actually like looking at the data sets because I'm an opportunist, and yeah, you could just immediately start working on there. So I think that that's some new interesting things to be thinking about in terms of how we frame things. And so with that.
Thank you. By the way, they probably submitted 30% of the request that comes to community catalog. So you have them to thank. If you see a lot of urban and Arctic type data sets, that comes from them. They're responsible. I love it when someone else sets the stage for me. I'm usually the person who comes in and does the methodology part. I'm like, okay, what exactly needs to happen when someone wants to move data into Earth Engine? What exactly needs to happen when someone wants to take a script and say, I want my lab to be able to publish this script outside Earth Engine because I can't really mint a DOI for a code repository inside Earth Engine. So what I'm going to show you is very hands-on approach of doing a few of those things. And there's a reason we wrote it as fairish principles, because a few of you might already have heard these terms in science in terms of findability, interoperability, reproducibility, and all of those things, right? So we want to talk about that very openly on, are these entirely reproducible? And the truth of the matter is almost very little of science is almost 100% reproducible. So that's why I want to stick to the idea of fairish principles. And what I'm going to show you over the next couple of slides is how to get to at least that bare minima and take it from there. And hopefully you're going to ask me questions, because I love the fact that you can ask me questions. I don't really have fixed text. I actually have almost no text on any of my slides, which is great, right? Let's see what I have in my first slide. Okay, so for most of you, what I'm showing right now is the idea that you can actually get to, I don't know if a lot of people know this, a lot of you can actually get to your repository by clicking on the gear icon, and you can actually go to a website, paste that link, and you will get to a Git repository. So what I did was I pasted that link here, and I went here, and I could actually get a Git repository. So what you could do from here is you can make a copy of all the scripts that are coming in to your Earth Engine source. So because I like doing hands-on, you will see me switching between slides and hands-on, and I hope that's okay. All right. So I wanted to show this, and I want to go into, this is just a sample repository we created just for this talk, right? And you can go to any repository you want. You can configure this, and when I click on configuration, you'll notice that it still gives me these links, right? You'll get two things. First is, if I wanted to accept this repository, I don't actually have the permission to share this with anyone else. The credentials are managed by other people, actually me, but still. And I can also git clone this. But git clone won't really work if you haven't really have Git established, right? And what exactly is Git in the backend? What it's doing is it's telling Earth Engine that, hey, you're writing some code right now. You're coming here, and I'm saying okay, I want to write some code, and there's some code right here that says example script. And I have two things. I have print hello world, print now. Someone added print now. It might have been Tirthankar, TC. So if I want to change this, or I want to basically go in, make an edit, and let's say you're collaborating with other people, right? This is the beauty of Earth Engine. You're collaborating with someone else. You basically said, hey, I've given you guys a repository that you can edit. Anywhere in the world, you can come into this repository, start editing, create a new code, and the moment you create this code base, I'll be able to see it. The moment I hit refresh, I should be able to see this. This is interesting. Why? Because when I hit save now, two things will happen. Okay. First of all, I'm not a writer here, so I'm just going to choose one of the repositories where I am actually a writer. You have to be a writer to be able to do this. So let me just go to one of my test examples somewhere. Okay, there's some open datasets examples here. Let me just go into one of these. And I'm just going to destroy this right now. And by the way, don't worry. Even if I'm going to edit this, I'm going to show you a way in how to bring this back, which should work. Gods of live demos, come on, work with me. Okay, let's do this. So examples, this is just an examples repository. Oh, I actually have a collection sort. This is great. So what I'm going to do here, I'm going to delete everything. I'm going to say print hello world. And then I'm going to say, by the way, did you know that you can do a console.log? It will allow you to actually run a lot of JavaScript functions within Earth Engine. So I can actually say console.log. This will also print the same message. And guess what? If I run this right now, you will get, ta-da. So you can use console.log or print. That's one thing, right? That's not the purpose of showing you this. But if I hit on save right now, you'll notice the gear wheel kind of rotating for a few seconds. Then if I go into this tiny little revision history, the last time I edited this was in 2022. Perfect. This was like, I think it was like right before the last Geo4Good because it was like the last week of September and like early October, that's when it was happening, right? It also shows me that there is some edit log. It gives me the time and things like that. Now this is actually useful. In Git, we have a function called git blame. I know that sounds really bad, but git blame actually allows you to find out who changed something when no one was looking. If someone goes in and accidentally says that I changed something and I shouldn't have, the owner of the repository has the capability of going back and reverting back. So let's say I have a compare. So I actually get a compare button. And I can actually say what's been deleted. Okay? Now, let's say that I was really upset at TC for deleting all of the things that I meant to kept here, you know? And I was like, okay, wait, what did you do again? And I want to revert this back. Two things can happen. One, you can actually see what they changed, which is really great. All the red is deletions, all the green is additions. And I can go back and actually click on the revert button. And it should theoretically go back to being the original code. Isn't that magical? Isn't that cool? Okay. This is one of those things that will be really useful for you if you're collaborating with a bunch of people, specifically a bunch of people who might be editing the same code accidentally, and they hit commit at the same time. Because then you can see what is the latest version based on the time logs, and you can see those details and they become really visible to you. You can take it multiple steps further to the point where not only can you like take this data here, like you can see these change logs here, you can actually click on the gear wheel that I was showing you earlier. And what I'm going to do is I'm going to copy this URL. Everything after the git clone, okay? So just copy that URL. And you can try this with anything you have a writer access to or owner access to right now. Paste it. Yeah, it'll tell me to log. I have tons of accounts. Ignore those. And then you can see a couple of things have happened. I reverted back, so all of the actions have hashes. I can actually see when that time at which I was reverted back, who reverted it back. If someone else was committing, I would see their change log as well. So if TC was committing, I would see last edited by TC or last edited by Aaron, which is super useful for me, right? I can also do something interesting. If I want a copy of the code, right, and I don't want to go and copy the what is of like, and for a lot of people, right, when you're importing, and I am sure everyone has this moment where they're like, oh, I have to copy the code, everything in here, but then I also have to click on this tiny button here to copy the assets that were important in the import bar, right? So in that URL, when you click on the masters tab, you have a log, but something more interesting is you have a zipped file. And that zipped file actually has your JavaScript code. So this is a way in which you can access your JavaScript code. So if you wanted to download and say, okay, my lab is ready to publish now. At this state, I want to download this JavaScript code. What can I do? This is one way for you to actually get to that. So as I was saying that you can take this really, really far, right? So I'm going to show you an example. I don't recommend everyone set this up, but I'm going to show you an example of what you can do with it. Okay, so I work on a lot of interesting things in Earth Engine. I have a runner, GitHub action basically, that goes in and says, every time I make a change edit, I have all of my repositories auto-sync. Every time I make a change in Earth Engine, it basically goes at midnight and says, I see all these changes. If there are changes, then I will commit them and copy this over to GitHub. This is really nice. Guess what? Something that's not actually exposed to you but available to you, you can also get pushed back to Earth Engine. So imagine that you have all of these codes that are available to you at a university. You're leaving the university now. You take all of these codes. You're starting a new Earth Engine, but you had these amazing tools. You have a zip file with all of these codes, but you want them in Earth Engine. You don't want to copy them individually. You can actually do a git push and push your entire repository back into your new Earth Engine account, wherever you are. So there's a bunch of things that you can do, and they're useful for you because they help with reproducibility. They go back to the point of like, if I am sharing, should I be sharing in this fashion? Should I be capturing those moments of like when someone made a change? Should I even make those logs available? And more importantly, I think the one thing that I know people love doing, and I love it too, by the way, it's a great feature. I want someone to debug my code. I click on the get link. I want you to remember these two differences. One is known as a state change. It's a state link, which means at this point, when I am editing this code, right, and I'm going to show you something. So I'm going to, again, delete this. I'm not going to save it. I'm just going to say, print hello world, sure. And I'm going to run this. And I don't actually have to run this, but let's say I want someone else to look at my code. I click on a get link, and I say, okay, I'm going to give this to a colleague of mine, and they paste that code, and print hello world comes up, and that's all fine and dandy. Let's say I don't actually save this, right? I go back to the original code, so there's nothing to save. So right now, my code is this. But the last snippet that you shared, the URL that you shared, doesn't give the users access to whatever is in the repository. So my recommendation for anyone sharing, like when you're sharing research or when you're sharing an entire code for like Earth Engine, don't share a get link code. Always share the repository. The benefit you will get is that as a user, if you want to add a new code, let's say you want created an app like TC showed, right? You can add that to the repository, and the only thing anyone in the world has to do is hit refresh or basically go back to the code.earthengine.google.com, and the new code appears magically on the repository. Because it's very nice for, in terms of maintenance, a user can still see if you went in and modified something, so that, like, let's say that someone sneakishly went and changed something, you can still see that. But it's a very nice way for you to propagate that change to everyone in the world. Really great for findability, accessibility, for interoperability, and most importantly, for the fact that there is a change log. There is provenance in how you did the code. Because there's more than just data provenance. There is code provenance. There's the methodological provenance, right? I'm a methods person, so I'm going to talk about methods. I love methods. Okay. So the next thing I want to talk about, and let's see where my slides take me, is getting data into Earth Engine. Everyone wants to know that, okay, suddenly I had Esri, I had QGIS, I had Eras, Imagine, Envy, right? And you want to switch over to Google Earth Engine. And one of the biggest concern, the quickest concern that people come up with, like, wait, I have this hard drive full of data, and I want to bring this into Earth Engine. Can I do that? Yes, you can. So as TC mentioned, yes, you can absolutely bring data into Earth Engine. And what they meant by that, every cloud asset or every project that you bring in has 250 gigabytes of storage space. It literally is free storage space for you to store your research assets. 250 gigabytes is the minima that you start with. There is a form on the developer's Earth Engine page that's called quota uplift. So if you actually search for it, you'll find it. There you can request that for your research, you need a quota uplift up to a certain amount. You can explain what you're researching and all of those details. And then they will, depending on like what the result is, they will generally update your quota. It's useful for researchers because, yes, 250 gigabytes might be enough for now, but as data sets get heavier and as you all get access to like a hyperspectral data cube would be like 25 gigabytes or more per image strip, you know? Just to give an example, NICE mission is supposed to have 10 terabytes of data daily. That's not launched yet, but it's going to be, right? Just to think about, like, if you get access to data sets like that, or when you're working with drone data. A lot of you are working with centimeter level drone data, extremely heavy data, right? And I know because I move part of like 80% of like open aerial map onto Google Earth Engine as part of the community catalog. So I moved like 8 terabytes of drone data into Earth Engine. And it was a massive process. And one of the things I learned is that even small looking images could be very, very heavy. So there is no relationship between, oh, it's a small footprint, it's probably not that heavy. No, it could be really, really heavy. So think about data needs ahead of time. A good way for you to think about getting data in is the code editor. As going back is like, yeah, you can click on the new, and you can click on upload GeoTIFF or shapefile or CSVs. If you really want to do a large amount of data uplifts, in one of the slides, which is the next slide, I'm not going to play this video. You can watch this video. This is a talk we gave last year on getting data into Earth Engine. There are 4 different ways in getting data into Earth Engine. Aaron was there for this talk. I was there, and Val was there. And we gave a talk on, like, if you have some cloud storage bucket somewhere, right? Maybe that'll help you, because if you have a Google Cloud Storage bucket, you can get data in. If you have data as cloud optimized GeoTIFFs already sitting somewhere, you can get that data in. Of course, there are 2 other ways of getting data in that I forgot to mention while we actually gave the entire talk. One is you create a request, and we actually gave the talk around that. You create a request with the master catalog people, which is Simon and team, or you create a request with the community catalog, which is me. And when you do that, we will try to see and evaluate, or at least I will try to see and evaluate if I can accommodate it in raster catalogs, like in the community catalogs. If not, I'll pass it to Simon and say, Simon, can you please help them? This is like 1 petabyte of data. I don't have that much space. So that's useful because that's important for you to know when you're getting data into Earth Engine. For getting data out, yes, there is two ways in which you can get data out right now. One is obviously the export function. The export function is the most common one. Please keep in mind that the export function does have limitations in terms of like how many export functions you can run, how long it will take for you to actually export the data out. But there is a very good talk, and I'm not just saying that because I'm co-presenting on that. There are other co-presenters, so go for them, don't go for me, you know? Like, they are presenting on 2 tools that will allow you to interact with the data as though it was present as arrays on your computer. They're called Get Compute and Get Pixels. These were 2 new things that were just introduced, really fresh from Earth Engine, and it'll basically allow you to interact with the data in array space without having to download the data. So I would recommend that we go to that one. Last bit that I'm going to touch upon, and then I'm going to give it back to Aaron, is sharing of data. I work with one of the largest populations of communities of researchers who have donated data to the community catalog. There's over 1,300 plus data sets, and I work with at least 5 to 6 researchers who want to donate data to the community catalog. And by the way, if you haven't gone to the community catalog, you can go to the community catalog and find data sets. These are data sets that are not in the Earth Engine's master catalog, but you can find them here. These are additional data sets, about 300 plus terabytes and about 1,358, I believe, last count. Something like that, yeah. So you can go here and find those. One of the number one things that I tell researchers is, please think for a moment about the license that comes with your data. When you are producing a research, most researchers will put it in Figshare or Zenodo or Dryad or, I don't know, some FTP in the middle of nowhere somewhere. I'm really hoping not in an FTP, but I'm really hoping that first they're following best practices in terms of how you're sharing your data. I'm a big fan of Zenodo because it does allow you for more control. And you can actually go to a Zenodo data share, and I believe I have TC's because I wanted to pick on TC. I took one of his data sets, and you will notice here a couple of things. One is you can come into Zenodo. Anyone can sign up. Anyone who has a GitHub account, it's completely free. It's maintained by the people who maintain CERN, so you know it's good stuff, right? And they have maintenance windows. Just ignore those. Those are like very short-lived on top, you know? But the good news is you bring in your zip files or your TIFF files, whatever you want. You arrange them in a structure that is readable. Please include a lot of information. I cannot stress this enough. I have seen data sets that literally says, this data set is for this paper, and that's it. No units, nothing, no more information about the band information or units or projection information, nothing, you know? So include that information when you're sharing data out. An important thing, I know as researchers it's hard to think about the fact that what is going to be the impact of data downstream, right? But I implore everyone here to say like, hey, if you think that your data is really going to change the world, make your data open source. And when you're choosing your license, spend like an extra minute just to read what that license actually means. There are some people who accidentally chose licenses that says ND, which means non-derivative license, which means no one else can use that data to build a derivative on top of that. It's not science that someone else can use. But if you put data under a CC BY attribution license, you still get the citations. And this is one of those primary things in the community catalog. You'll notice that every time I go into a data set, so I just uploaded the FabDem data set to version 1.2. Erin made the request a couple of days ago. You'll notice there is a citation. And this way I can cite you, I can talk about the license that is here. Now FabDem may not have been the best license to show for this example because it actually is under a CC BY non-commercial license. But if I go to the ones that I just uploaded today, I uploaded 2 data sets today. And if I go into changelog, which will be, I uploaded 100 years worth of global earthquake data sets. And this is, because it's USGS, it's under open data licensing, and you can actually look at the counts of these data sets. You can actually look at the example scripts and so on. This really helps. Adding this license terms really helps the next person to use your data, and that will also get you more citations and improvements. I think that was the last slide for me. I am going to pass it back to Erin. And I'll go to slideshow. And please talk to me if you have more data needs or just want to talk in general about strategies. Yeah.
Thanks, Sam. I think you move more data than anybody else I know, so especially research data, which I really appreciate. So we're going to take some time to talk about ethical considerations and engagement. Yeah, super important. So we talk about this in the education paper, but I thought it was worth going back over at this presentation as well. When we talk about impact, impact is obviously like what we're here to talk about. But I would say that what goes hand in hand with impact is also ethics. And the best piece of advice that I could give you today is that we do not spend nearly enough time thinking about the ethical considerations, especially as we do high impact work. And so 3 ways that we've broken those things out is to think about individual considerations. And so those are things like accountability, transparency when handling sensitive data, especially in the cloud. Consideration number 2, we've termed social. And so those are things like human dignity, justice, public good when collaborating with communities using Earth observation data. And then the 3rd one is subject. And so those are principles of trust, stewardship, integrity when we're representing remote sensing data and inferences. And so I want you to just take a second and think about your own work and your own intentions and think about how much time you've ever spent thinking about these 3 concepts. And I've had the opportunity for the past couple of summers to spend time being a team lead for the University of Washington Data Science for Social Good program. And one thing that program really made me appreciate is that we spent a lot of intentional time as a team talking about these concepts and putting them into action. And they informed our topics from the get-go. We talked to stakeholders, we talked about our internal components, we talked about the visualization. We really did go through a lot of these dimensions. And it's not something that I think we can be perfect at. It's not something that we necessarily even have a solution for at the time. But I think that the first step is to really take the time to spend some time thinking about it and discussing it amongst ourselves, and then starting to write about it as well. And so I thought I'd put up a couple examples. Some of these are a little bit informed by my own work. So we've done a lot of thinking about individual ethics, especially in relation to data sets in the cloud. And so this is a picture, a screenshot of the USA structures in Washington, D.C., and this is a data set that I actually use for my own work. And part of why we use it is that we're doing heat pump and also estimating heating loads at the building level. And so one thing that we talked about in my team is that can make people feel really uncomfortable. It makes sense from a geospatial standpoint. So it makes sense that we know that people's houses vary. That feels like the right unit of analysis. But I always try to take a step back and remember that you're talking about people's houses. You're talking about there is some data that I've been using that has been de-identified, which is good, but we're trying to re-aggregate it back to the household level in order to bridge some of these individual ethics issues. And so they're really key to be thinking about, especially as you go into finer spatial resolution. What are you really looking at? And who might care about that? And especially as a geospatial scientist, we always want to have the geospatial location on that, of course. But with some information, is that really the best way to handle the information? And for this housing work, what we're doing is that our goal is to not perfectly model what's in your individual house. It's to create a representation that gets close enough for the type of work that we want to do, but doesn't actually represent exactly what is in your house, because that's a privacy violation. So these sorts of things are becoming very real, and they're important to think about. The second one is the social ethics. And so those are their interpersonal principles, and like I mentioned, including things like human dignity and social justice, following laws on data use, and promoting public good. And so this is a new data set that came from the community catalog. It is some USGS historical imagery, and I happened to just come to the scene accidentally, but it's of Bodega Bay in California in 1960. And so this is a really interesting scene because they actually tried to put a nuclear reactor here, and the community had a huge protest against it, and apparently the first hole that they started to drill had massive flooding, and so they were able to shut it down. But I think the thing to always keep in mind when we're looking at these images is that what does it actually look like on the ground? How can you actually impact things? What is your own personal perspective? Are you coming at it with altruism? And are you able to actively engage marginalized groups? And are you thinking about identifying potential harms from applications? And so geospatial data has a lot of power, obviously with the defense applications, but it also has a lot of power to do good. And so the last one is talking about subject ethics. And so those are things like false precision, map seduction, types of errors, and responsible accuracy for communication. And so this is really key when working with machine learning, when biases can emerge from sampling, deficiencies in tuning, and then, of course, local knowledge gaps are key for subject ethics, especially in representing Earth observation capabilities. And so I put this picture up. This is some Maxar data, actually, from the Afghanistan earthquake in 2022. Of course, people are probably going to do work on it. This is a really, especially when you're dealing with hazards, especially when you start to get into doing hazards and machine learning, which is a good idea. It's important to really keep these subject ethics at the forefront, as well as those individual and those social ethics, and really be cognizant about how you're communicating, acknowledging what happened, are you missing anything? And really appreciating the variety of technical, emotional, and decision-making aspects that go into the type of work that we're doing. So, TC.
Thanks, Erin. So I'm going to close us out and kind of expand the idea of impact a little bit, because we have been focused a lot on, and that kind of follows what Erin was talking about in terms of ethics. But first thing, kind of a lot of these high-impact journals, general interest journals, the good thing is that the editorial process is very fast, so you generally will know if they don't want it pretty fast. And sometimes it gets rejected after peer review, which sucks, but if it went to the peer review stage, it means that your initial idea was correct, that it is something the editors liked enough to send it out for peer review. So the review process itself can then be a learning experience. So I'm just giving some examples of a few papers which kind of went through a lot of, these are cases where they actually went to peer review and we received the reviews. And they all went into good journals. Sometimes they went into journals which are like technically higher impact factor than the original papers. And this has happened a lot where a paper will get rejected from a seemingly low impact journal, but then get published in a higher impact journal. So there's a lot of uncertainty in that, and I wouldn't deal too much with like individual paper rejections or why a particular paper didn't go through. And I think on a broader scale, a paper is a paper, but the idea is you are trying to advance science, you're trying to advance knowledge, and you're trying to advance how we use that science to improve society, especially in our field. And with that, like, it is important to understand some of the uncertainties with some of these, particularly in this case, geospatial data sets. So this particular plot is for future projections of urbanization. And they're all like projections based on different assumptions of areas and different empirical models and different historical data sets that are calibrated, that those data sets are calibrated against. And you can see like these large differences. And we expect these differences. Uncertainties are normal, and I think it's important to think about uncertainties and talk about them more broadly. And I personally feel uncertainties are not talked about enough in high-impact journals. And part of that is because you want those flashy headlines, you want those newsworthy articles. I have seen so many papers where someone does an analysis using one global data set, and maybe the results would have been same with another data set, but it's hard to know when they don't do that, when they don't do any sensitivity analysis. So for instance, here, if you have very different quantification of future urban area, that can impact a lot of your estimates for future risk. And ultimately, it does come down to not just the papers being published, but actual impact on the ground and actual like risk assessments and how it affects people. Another example, and this is an app as well for this, but when there are 3 10-meter data sets came out in 2020, and I did a lot of kind of comparisons for the urban area, and what I found was they were very different, and that's again expected. When you consider these different data sets, they use different methods. I don't know if you know, like this, the Esri land cover, the ESA world cover, and the dynamic world data set. They have different assumptions of in terms of like training data. They use different methods. The ESA data uses the random forest algorithm, and the other two use UNets. And they also have very different typologies for land cover class. For instance, if you look at the dynamic world paper, you will see urban is considered built up with nearby vegetation, which means that you shouldn't necessarily use this data set to understand, say, urban vegetation. However, I think dynamic world is interesting because it also has probabilities by pixel, which means you could create new thresholds to do that. You cannot actually do that with the SG data set. On the other hand, with the ESA data set, you generally can. And I didn't show it here. When you compare these different land cover data sets, and there are probably like 20 now at below 100-meter resolution, there's a large amount of difference. So you can write a paper using one data set and say like risks are increasing. But if your primary goal is risk quantification, your choice of data set would have a huge impact. And that risk quantification goes to policy making, it impacts policy making, it impacts, say, if you're using that data for insurance rates. So we need to be a little cognizant about like how it impacts beyond your high impact publication, especially with large scale geospatial data sets, which are not necessarily calibrated for regional to local scale applications. So with that, I'm gonna kind of stop. I think we are good on time. We have like probably 5 minutes for some Q&A if you have any questions. We have some mics. Oh yeah. Maybe we can use them. Okay. Yeah, like 3 minutes. I think they're recording, so it would be nice if you don't mind. Yeah. Can we turn this one?
Thank you for the great presentation. Great presentation. First, was really nice. And there was a lot of great points that were mentioned. And I don't know, I don't have a formalized comment, but maybe a question to you three on how, so that comes back to the first part of the talk and the last part, actually. How do you think the review process could be modified, improved to reduce the negative effect of these uncontrollable factors associated with the publication of a study? And I'm asking that question because I don't, and maybe you are the right group to suggest that. I was hoping, I think a lot of people have a lot of ideas to make things better. But they don't talk enough about those ideas, and I was hoping maybe we could create a survey where scientists can provide feedbacks on the review process, because I think this is something, a subject very dear to a lot of people, and a lot of people have a lot of ideas about it. And so I think creating a platform, a public platform where people can really talk about those issues and drive like improvement would be awesome. But what are your thoughts? And one of the effect of these uncontrollable factors, I think, is, as you said, the fact that we don't talk enough about uncertainty. I think it's changing. We are talking more and more about it. But the question remains of what do we do with that uncertainty? Now we have ways to quantify it. Funding offices have pushed us to think and quantify those, but what do we do with these uncertainties now, and how we communicate about those? Any ideas?
Yeah, I think the first thing regarding review, it's always tough to fix peer review, I think, at this stage. I know there are particular journals trying to, you have like journals which have all the reviews being public. But in many cases, you still have options to kind of opt out of that. So sometimes like making that mandatory would help. But I think what happens now with so many journals kind of fighting for space is that people will then kind of go to other journals where that's not mandatory. The other thing to kind of keep in mind is that our current scientific knowledge is the result of things that were correct, that we found out after like decades. But while we are living through the scientific process, it always seems like everything is talked about a lot more, partly because of there being a lot more social media where you kind of can talk about your work, and also like this focus on news articles. So I think it's important to kind of take a step back and understand that individual papers don't necessarily have to be correct. The point is like we need to move towards understanding through like multiple lines of evidence and like overwhelming evidence. A single paper is not going to provide that. And I think we need to like stop focusing on individual papers when we think about science and scientific progress.
To answer your question, any time that I think the paper review process is bad, I just remember what the proposal review process is like, and that could be even more problematic. One thing that I found that's an overwhelming issue is that just reading something once is typically not enough to actually be able to review something well. And that's a really big issue. And then you need to be able to like read it at least a couple times and then think about it and then figure out if there's any like really large flaws. I think it's a place that, although we worry about large language models taking our intellectual property, they do have a large capacity to be able to go through documents and answer some of those simple questions, and as a reviewer point you to the right places much more quickly. And so it helps remove some of the bias if you're using it in an educated way. So I think that that's like a real opportunity, but I also think that there's a lot of intellectual property involved and that it's not quite a simple answer. But I'm less concerned about the intellectual property than I am about people just simply not reading things. I think that that's the bigger issue in my experience. So.
I think we are at the time. So, okay.
So I have just kind of like a provocation. It's quite a sensitive topic, I guess. I always found very elitist the whole academia thing and how we review paper. There's a huge inbreeding of ideas, and we know that very well. And I think just the fact that lots of more technical people, they are very well included and engaged in the technical part of the development of a project, but not exactly in the writing, and way less in reviewing, for example. So it's very rare that we have technical people really reading through the method and really checking things. So I was just really looking forward to hear a little bit more of your impression of how much of this is kind of like captured, how much of the peer review with high quality of the technical part of our research is really done when considered this kind of like business as usual way of reviewing papers in the academia, very often excluding the technical people. Technical people is a terrible terminology, by the way, but you got my point.
Yeah, by technical people, are you meaning like methods people? Yeah. Right. I mean, I think the peer review process is generally not expected to figure out technical issues unless they are like fundamentally opposed to what we know in the field. I have had cases where someone has, a reviewer has actually gone into my data, analyzed the data, and pointed out it's an issue. There are issues. And that is very rare. And you have to also kind of think about like reviewers don't get paid for this. So it's kind of like a self-perpetuating kind of cycle where, especially now, if you look at some of the reviews being published, like I review a lot of papers and I see some of the other reviews and there's very little information being actually, or feedback being provided. But I think that's kind of goes back to the fact that we should not be using individual papers to judge leaps in the field. Ultimately, the point is you should have multiple lines of evidence pointing to the same results from multiple groups, which is when you can be more confident about those results. Because individual groups can make mistakes. They can fabricate data. That does happen from very big groups. And individual groups may also be mistaken about something, not like due to technical error, but because they don't understand something. So that's why you need multiple lines of evidence, I think.
Yeah, I think what you bring up in terms of the technical review is something that, and going back to your point, Helene, that we could do better for sure. I have definitely got into people's data and looked at it and pointed things out. It was a pain for me to do that, but I didn't. I read what they wrote and I was like, that's true, but like, is it really true here? And so I totally went and looked. So I think when we were talking about the Farish principles, the open data, the code availability, those are things that as projects get bigger, as like the core competencies become larger, that's something that we need to be thinking about, is not just having one person review necessarily, but having like a few people review. And you're reviewing the code, you're reviewing the data, you're reviewing the like paper itself, you're getting that holistic version. And it definitely happens internally in groups. And that's really helpful. But a group can only see so much is the thing. And having that like external component is really valuable. And so I know I've really appreciated all the education work that we do, because that's a public code review. and it's a good chance to be able to like think through your ideas in places that you know people will see. And so when we think about like high impact peer reviewed research, especially with Earth Engine, like if you have intermediate skills, you should be able to go into their code repo. You should be able to understand what they're doing, how they're doing the analysis, and hopefully see something that you can use. And so maybe it's not from the paper itself, but it's from how they technically use the data. And if you're doing that, it is really nice if you're citing and like acknowledging that. And so I think that's part of the other issue is that we're tracking if you cite the paper, but we're not necessarily tracking, and we track if you cite the data, but we don't necessarily track if you cite the code. And that is equally important in our knowledge economy now. So.
And I'll add one last thing as a person who loves methods. Yes, do the fairish principle pieces that we said, because we want there to be reproducibility. Share your data. Most journals have hogged up and put papers behind paywalls with $35, click here to purchase this paper. At least make the data public and write as much quantity. You know what? Just copy the whole paper and put it in the dataset description. They might want to read the paper, and they might actually have access to it. And the other thing I would like to say is that there's something very interesting I learned. I used to write a lot of open source software when I was in college. Funnily enough, when I was actually doing my thesis defense for my PhD, I never got to include those as contributions to the scientific community, because they said that it's not really peer reviewed. And I said there's 86 version releases of this. There are 122 solved issues on this. There are reviews done by hundreds of people around the world. This is how things like the Linux kernel was formed. And this is how Linux actually is maintained. There's hundreds and thousands of open reviewers who can access the code and do this. Science needs to also evolve with this idea that the 3% review should be dead. It should be a public review.